Hello everybody. In this lesson, we will introduce Laplace Transform. This is a very powerful tool for classical control because through Laplace Transform, we can transform the differential equation into an algebraic equation. And you know that most of the engineering systems is governed by differential equation. Dealing or practicing differential equation with its sophisticated mathematics will consume us a numerical effort. So we go through the Laplace transform to get rid of the differentiation, and we transform it into algebraic equation. So let's start with the definition of Laplace transform. So starting with the definition, we will find that f of s equal the integration from 0 to infinity, the exponential function to the power minus st times f of t dt. So this is the function that we have in time domain. So we will transform it into S domain. This is, we will call it the frequency domain, because in general, S is a complex number. It is equal sigma, which is a real number, plus J. This is a complex number, which is root minus 1 omega. So this is the general formula for S, sigma plus J omega. So when plug in your f of t into this equation will transform it into f of s. And we will show you how to transform the differential equation into algebraic equation. Let's start with the first example. Let's have f of t equal 1. So applying this definition to the current function, so f of s equal the Laplace transform of f of t, which is 1. Okay, this is a symbol for Laplace. It acts as an operator on the function, which is in our case 1. This will equal applying this equation. So the integration from 0 to infinity, e, which is the exponential function to the power minus st, times f of t. In our case, f of t equal 1, so times 1 dt. So this is a simple integration. The integration of e to the power minus st is the same, e to the power minus st divided by s, or minus s in our case. Okay. And this should be substituted with the limits from 0 to infinity. Applying the infinity, e to the power minus infinity equal 0, minus applying the 0, so e to the power 0 equal 1, so minus 1 over minus s. So this minus times this minus 1 will equal positive 1, and the result will be 1 over s. So the Laplace transform of 1 from now on will be 1 over s. So we will not go through these details anymore. Once you find 1 and you are asked to find the Laplace transform of 1, you will put directly 1 of s. Let's see example number 2. Example number 2. let's have f of t, sorry, f of t equal e to the power t. So applying the same equation, the same transform equation. So now Laplace of, this is the operator of e to the power t equal the integration from 0 to infinity e to the power minus st times f of t. In our case, f of t is e to the power t. So combining the exponents, we can have integration from 0 to infinity, e taking minus as a common factor, okay, from here. So we will have s minus 1 all times t dt. So it turns into a simple integration, which we can perform easily. So the integration of any exponent is the same. So it will be e to the power minus s minus 1 t over this minus s minus 1. And the limits from 0 to infinity, this will be very easy, taking this denominator as a common factor. So we have minus 1 over s minus 1, substituting with the infinity, e to the power negative infinity is 0, 0 over anything will be 0, minus, substituting with 0, e to the power minus 0, it will be s will be substituted by 0, and negative times negative will be positive, so it will be e to the power positive t, okay, and t is substituted with 0, sorry, when t, because we are integrating with respect to t, so t is substituted by 0 in our case, so e to the power 0 will be 1, and the denominator will be as it is, so it will be negative 1, and the denominator is taken as a common factor for the two terms. So finally, we will get the result to be 1 over s minus 1. So from now on, if you have f of t in this form, e to the power t, so directly we will put, if you are asked to get its Laplace transform, you will put this expression 1 over s minus 1. So let's go on and have more examples. Our current example will be, we are asked to get the Laplace transform of e to the power negative at, where a is a positive number, any positive number, times f of t. So now we have an f of t, but this f of t is re-multiplied by e to the power negative at. So let's apply our definition of Laplace transform. Don't forget this definition. F of s equal integration from 0 to infinity e to the power negative st times f of t. Take care, our current f of t is not only f of t, is an f of t multiplied by 3 multiplied by e to the power negative 80. Let's apply the definition. So it will be equal the integration from 0 to infinity e to the power negative st times f of t. Our current f of t is e to the power negative 80 times f of t. So let's handle this multiplication. We will combine the exponents of these two exponential functions. So combining them together will be equal from 0 to infinity e, and taking the negative as a common factor, and t is a common factor. So we will have in the bracket s plus a here, and f of t will be written as it is, d of t. Now, when we look at this integration, it's little bit like the original integration, this one. Okay, let's make an analogy between these two definitions. I think they are the same, except that s is replaced by s plus a. Okay, so let's define a new parameter. Let's call it s hat equal s plus a. So now we can rewrite our last expression, which is we have Laplace transform of e to the negative at times f of t according to this definition. So it will be equal the integration from 0 to infinity e to the power negative s hat, where s hat equal s plus a is s hat t f of t dt. So comparing this expression with this one, it is the same. The only difference is s is replaced by s hat. So this will equal, if this expression is equal to f capital of s, so this expression will equal to f capital of s hat. And s hat is f capital of s plus a. What does it mean? It means that if you have an f of t, if you have an f of t that you know already its Laplace transform f of s, and this f of t is pre-multiplied by e to the power negative any positive number t, the new Laplace transform will be the same, that you know about this f of t, but each s in your known expression will be replaced by s plus a. Let's see an example. Okay, this is a new example to apply this feature of Laplace transform. So this is a very useful feature. So we know that the Laplace transform of sine omega t, if we know that the Laplace transform of sine omega t will be omega divided by s squared plus omega squared. And we can prove this expression by the same definition. Okay, but let's this time, this is a given expression. Someone tells us that the Laplace transform of sine omega t equal omega over s squared plus omega squared, and this is right. Okay, now we are asked to find a Laplace transform of e to the power negative a t sine omega t. So now we can apply this feature of Laplace transform. Now we have an f of t that we have already known its Laplace transform. In our case, is sine omega t, and we know the Laplace transform of it. It is already given. And now we are asked to get e to the power negative at times this one. So the answer directly, according to the last proof, is it will be f capital of s plus a. So what is f capital? The f capital is the Laplace transform of sine omega t. So we can write this expression that we have already know, omega over something plus omega square, and each s in the f capital of s will be replaced by s plus a. So the definition will be, so the answer will be s plus a all square. What is this expression? What is this term? This is the same that we already know, okay? But each s is replaced by s plus a. Is it clear? Okay, let's see another example. And let it be a numerical example. So what's the Laplace transform? If it is given that the Laplace transform of cosine 2t equal s over s squared plus 2 squared. This is the Laplace transform of cosine 2t. So in general, cosine omega t equal s over s squared plus omega squared. Okay, this is one of the very common Laplace transform that we should keep in mind. Okay, we should keep the Laplace transform of sine omega t and sine and cosine omega t. Okay, this is very common, and we will use it frequently while we are using while we are dealing with control systems in engineering in general. So now we are asked to, what is the Laplace transform of e to the power negative 3t times cosine 2t? So we repeat the same feature of Laplace transform. This is our f of t that we have already known its Laplace transform, this expression, and now we are asked to get the same function but may be multiplied by e to the power some constant t. So the answer is the same that we have already known, will be s, but s will be replaced by s plus a. In our case, our a is 3. So it will be s plus 3. This is the s hat in our case, divided by s plus 3 all square. Okay, this s plus 3 is replacing that s plus 2 square as it is. So this is the answer of our new function f of t. Okay, is it clear? I hope everything is clear till now. As we said before, that the most important feature in Laplace transform that it converts the differential equation into an algebraic equation. So let's now see this feature and prove it, because it is the most important one. Let's share the screen. So let's have a new page. So now we are asked to get the Laplace transform of df of t by dt. So this is the derivative of f of t. So we know that the Laplace of f of t is equal to f capital of s. So now we are asked to get d by dt f of t. So it will be equal directly s times f of s minus f small of 0. Let's interpret this expression. So s, this is the frequency domain variable, s, okay, times f of s. So f of s is what? This is the transformation of f of t. So we know that the Laplace transform of f of t, where f is small, equal f capital of s. So when you see f capital, it means that this is the Laplace transform of f of t. But now we are asked to get the derivative of this f of t. Okay, so it will equal to s times f capital of s, which is the Laplace transform of f of t alone without the derivative, minus f small of 0. What does it mean? It means that you get the f function, f small, it means that the function in time, f of t, and replace each t with 0. So now we have to prove this uh, this result. Okay, how to prove? So the proof will be as follows. Let's change the color. So now let's apply the definition of the Laplace transform. Don't forget, the Laplace transform of any function uh, in time domain will equal to the integration from 0 to infinity e to the power negative st times f of t d dt. Okay, so we will apply this definition to our case. So the Laplace transform of d f of t by dt will equal the integration from 0 to infinity to what? E to the power negative st times f of t. In our case, f of t is df by dt. df by dt. Okay, we can do it by when you find the derivative in the integration. So integration by parts will help us. So integrating by parts. Can you remember the integration by parts? So this is the integration of u dv equal uv minus the integration of v du. So this is our u and this is our v in our case. So it will be u v, so it will be equal to, this is u as it is, v, it means that we have to integrate dv, okay? So this is df of t, it will be f of t. The integration of df of t is f of t, and put the limits from 0 to infinity, applying the definition, minus the integration with the same limits from 0 to infinity, v du, v du. So v will be put as is, f of t, here it is, f of t, and du, it means that we have to differentiate u. In our case, u is e to the power negative st. So by differentiating this term, it will be negative s times e to the power negative st. Okay. So let's substitute. So e to the power negative st and the integration with respect to s. So applying this infinity here, it will give you 0. The first term will be 0 because e to the power negative infinity 0 minus substituting with 0. So this will be 1, and that term will be f small of 0. Take care that there is a difference between f small, which is the function itself in time domain, and f capital, which is the function in s domain, the frequency domain. So this is the first substitution, okay? And this minus will be multiplied by this minus to be plus, and the integration with respect to dt, I forgot what this to put this dt. So s is not a variable of integration, so we can pull it out. So s can be here, and this is the integration from 0 to infinity e to the power negative st times f of t dt. Okay. Have you seen this term before? Sure. This is the definition of Laplace transform. This is the main definition of Laplace transform, which is equal f of s. So we can replace this term. Okay. Let's change the color. So this term equal f capital of s. Okay. So now this is s multiplied by, let's save the space, s multiplied by f of s minus f of 0. And this is what we have started with. Okay, this is that we have started with. So keep this in mind. The Laplace transform of any derivative is just s multiplied by the Laplace transform of the function itself without the derivative. Okay, and for initial conditions we have to subtract this f of 0. Okay, so let's continue to the second derivative. Okay, it will be very cute. Okay, you will find it very cute. Similarly, let's change the color. Similarly, the Laplace transform of the second derivative e of t by dt, we can write it like that. Laplace transform of d by dt df of t by dt. Okay, so this is the second derivative. But from a while, we have already proved that df of t by dt, the Laplace transform of it is equal s times f of s. So now it's a new derivative to a function that we have its Laplace transform, which is the following. This is the Laplace transform of df of t by dt. So we can deal with the new problem as the same as the last one, except that the function that inside the derivative operator is the derivative itself, and we have to add a new operator as a derivative. So we can write that it is the same. It is s f of s. What is f of s? This is the Laplace transform of f of t, right? So in our case, it is the Laplace transform of df of t by dt, which we already know. Okay, which is already known. The Laplace transform of this one is the whole expression. So it is s times this whole expression, s f of s minus f of 0. So this is the Laplace transform of df of t by dt, okay, minus the function itself at 0, okay, f small of 0. But our new function is df by dt. So the derivative of the function at 0. So because this is the function itself, so it will be f dash of 0. Dash means the derivative. So simply, if we arrange the terms, s times s will be s squared f of s minus s times f of 0, s times f of 0, okay, minus f dash of 0, and so on. Similarly, in a general form, we can extend our proof that the Laplace transform of the nth derivative of f of t by dt to the power n equal s to the power n. Okay, you can keep track the division and make it yourself, but it's very clear because when we start with the first derivative, we ended up with s times f of s. The second derivative, we ended up s squared times f of s. So the nth derivative will be s to the power n f of s minus s to the power n minus 1 f of 0. Take care here, s to the power n minus 1, and the n in our first case was 0. So s to the power 0 equal 1 times f of 0. That's we have already done in the second case, that s to the power n minus 1, in the second case is 2. So 2 minus 1 is 1. So s times f of 0, okay, minus s to the power n minus 2 f dash of 0 minus s to the power n minus 3 f double dash of 0 minus, and so on, till this is the previous, not the last term, this is the previous one, s to the power d, the derivative n minus 2 f of 0 over ds n minus 2, and the last term is d n minus 1 f of 0 over ds minus 1. So in the first case, the last term was the derivative of n minus 1. This is the 0 derivative, so it is the function itself. In the second case, where we have started with the second derivative, so the last term was dn minus 1, so it is the first derivative at 0. And in general, in nth case, we will end up with the last term to be d to the power n minus 1. So we have to take care of very important note here, that if you take care from the first derivative, that when we have the first derivative, it is converted to a multiplication. The derivative with respect to t is transformed